Bismillah Rahman Rahim. Dear students, welcome to the course of Artificial Intelligence. Today we will discuss lecture number 14, and the main topic of the lecture is learning types. So, in the first lecture number 13, we discussed about learning, but in today's lecture, we will discuss some of the types of the learning. So, this is the main topic. This is your teacher Tariq Aziz, lecturer at Institute of IT, Kohat University, HANGU-CAMPUS. So, let's move on to the agenda. Dear students, agenda for today's lecture is the symbol-based learning. There are different types of learning. So first of all, we will discuss the symbol-based learning, and then we will discuss the rest of the learning types. Dear students, symbol-based learning, as its name suggests, here we will use symbols to learn. So in the first point, it says that we live in the world of symbols. Human beings, what they do, they use symbolic representation or interpretations to understand the world. Now, for example, we say that we saw a mainframe computer of the size of a room. So, what we are doing here by using the analogies of symbolic information, we are trying to associate things with one another. So, in this case, we are trying to associate the size of the mainframe computer with the size of the room. So, what we are doing basically, we are performing the symbolic representation. Now, similarly, the techniques we are to learn now use symbols to represent knowledge and information. Now, previously, we discussed about the rote learning, we discussed about the inductive learning and the deductive learning, but now our learning technique is different. So, here in this case, if we want to represent knowledge, if we want to represent information, then we will use symbolic representation or we will use symbols. So the first thing is that what if you want if we were to learn the concept of a good student. So previously we discussed about a good student and a bad student. So the problem is we want our learner to know that which one is a good student and which one is bad student. So if we want to keep our problem simple, then we can label all the students who are not good with the average, below average, satisfactory, bad. So all those students we can label them as not good student. Now we will use two attributes to define a student, and one of them is the grade attribute and the second one is the class participation. Based on these two attributes, we will try to identify that whether is the student is a good student and not a good student. Dear students, most of the time I am using the term we. So here in this context, by we I mean our machine, because we are discussing the machine learning. We want to teach our machine, we want that machine should be capable of learning. So don't confuse yourself. By we means the machine, our learner. Okay. So here machine will use two features, the grade and class participation, and based on these features, machine will try to differentiate that whether student is a good student or not a good student. Now, dear students, these attributes can have either of the two values, high and low. Okay. So now, look at the uh, patterns. Student, good student, when. Okay, so we can say that this is a rule. Okay, we discussed rules while we were discussing our lecture programming with Prolog. So it's same thing. Okay. It may not be 100% same, but just to give you a better understanding, so you can think that this is a rule. Okay. So student is a good student if his grade is high and his class participation is high. The second pattern can be student is a good student if his grade is high but class participation is low. He is not a good student if his grade is low and class participation is high. He is not a good student if his grade is low and class participation is low. So these are the some of the patterns. Okay. Now, dear students, here from the previous slide, you can see that the system is composed of symbolic information based on which the learner can even generalize that a student is a good student if his slash her grade is high, even if the class participation is low. Okay. So what are these? These are the symbolic. These are the symbols, or we can say this is the symbolic representation of knowledge. Now, by using this knowledge, our learner can generalize that if the student grade is high and his class participation is low, even though the student is a good student. So this is the rule. Okay. This rule are learner generated from these rules. By using these rules, okay, our learner uh, generalize a rule like this, that a student is a good student if his grade is high and class participation is question mark. So this is a new rule which our learner learned and then added to his knowledge base. Now we can say that our machine is learning. So this is called the generalization. Okay. Now, dear students, this is the final rule that the learner has learned from the enumerated examples, as I discussed a couple of minutes before. Here, the question mark means that the attribute class participation can have any value. It can have the value low, it can have the value high, as long as the grade is high. So here in this case, this question mark means that this class participation can have any value. It can have the value high or it can have the value low as far as this value is high. Okay. Now, dear students, we will see all the steps. We just saw some of the, we can say we just saw some of these steps, but not all of them. But now we will see all of these steps the learner has to go through to actually come up with the final conclusion like the previous one. Okay. Now, dear students, the here it says that how learner uh, generated this new rule or how learner learned this new rule. So we will go through all these steps one by one. So the first step is the problem and the problem spaces. First thing is to understand what the problem itself is. It's very necessary, and we already discussed this concept in our problem solving lecture. That first thing is the problem definition, the problem statement. You have to clearly identify the problem statement. So here it says that the machine has to understand that what the problem itself is. So in theoretical computer science, there are two main branches of problems. One is the tractable problem and the other one is the intractable problem. Now what are these? Okay, those problems that can be solved in polynomial time. So we have two times. One is exponential time, which grows exponentially, which grows very fastly. But the other one is the polynomial time. So those problems, I would suggest that you should search the internet for these two terms, the polynomial time and the exponential time, and then you will be able to differentiate between them. But exponential time grows very fast. Okay. Now, dear students, those problems that can be solved in polynomial time are termed as tractable, while the other half is called the intractable. Okay. But we can, it says that the tractable problems can be further divided into structured problems and complex problems. Structured problems are those which have defined steps, okay, through which the solution to the problem is reached. So in structure problems, as its name suggests, there will be defined step, there will be some structure, and you have to follow this structure to solve the problem, okay, to reach the conclusion. but the complex problem, they don't have well defined steps. Okay, so we can say that this is the difference between the structure problems and the complex problems, that the structure problems will have well defined steps, but the complex problems, they don't usually have well defined steps. So what about the machine learning then? It deal with which type of learning? Machine learning algorithms are particularly more useful in solving the complex problems. For example, the recognition of patterns in images or speech, for which it's hard to come up with the procedural algorithm otherwise. So problems like, if you want to recognize image, if you want that our machine should recognize image, our machine should recognize the speech, okay, of a person, okay, then these problems we cannot have a procedural algorithms. Okay, so these are not well defined problems, or we can say these are ill structured problems. So for these problems, what we will do, we will try to use the machine learning algorithms. Okay, now dear students, this is the okay, here, so this was something about the problem. First of all, you have to define the problem, that which sort of problem, for which sort of problem you want to use the machine learning algorithms. Dear students, look at this heading. We have two part in this heading. The first part is the problem, and the second part is the problem space. So we just discussed this problem, that we have different problems in our society, in our world. Okay, so but here we just discussed these in context of machine learning. But let me summarize in one line, that we are dealing here with the complex problems, and we want to develop algorithms, or we want to develop machine learning algorithms for our complex problem, because these problems are ill structured problems. We don't have well defined steps for these problems. So we just covered this part of the heading. Now what about the problem spaces? What do you mean by this? The problem space, or we can say the problem domain, this is the example of the problem space. So health is one of the problem domain, or health, we can say it's one of the problem space. The problem in this case is to distinguish between a sick and healthy person. So as an example, we will take this domain, which is the health domain. So in this case, we want to differentiate between a sick and a healthy person. So suppose we have some domain knowledge. Keeping a simplistic approach, we say that two attributes are necessary and sufficient. As we discussed attributes and features for a good student and a bad student, so with respect to dom- domain of health here, if we want to know that whether a person is sick or it's a healthy, so for this purpose, we will use two attributes to declare a person as healthy or sick, and these attributes are the temperature, which we will represent with the T, and the second one is the blood pressure, which we will represent with BP. Okay, so based on these two features, based on these two attributes, we will try to identify that whether a person is sick or healthy. Now, patient coming into the hospital, we can have three values for temperature and blood pressure. It can be high, represented by H, it can be normal, represented by N, and it can be low, represented by L. So both of our attributes, the temperature and blood pressure, it can be either high, normal, or low. So based on these values, the person is to be classified as sick. But here it says that so we representing sick with SK, and at this point it says that sk or sick is a boolean value. Okay, so if sk is equal to 1, it means that person is sick, but if sk is equal to 0, it means that person is healthy. So the concept to be learnt by the system is of sick, that is sk is equal to 1. So this is the basic concept which we want our learner to learn. Okay. Now, dear students, what is the instance space? Okay. Uh, how many distinct instances can the concept sick have? So we have a table here. We have two attributes. One of them is the temperature, the other one is the blood pressure, and we have three values for each. So how much possible values we will have? So we will have a total of 9 possible distinct instances in all. So if you look at the table, then this is our instance x, this is the temperature, this is the blood pressure, and this is the sick. Okay, this is our concept. Now here, if the temperature is low, the bp is low. Okay, temperature can be low, bp can be low, then temperature can be low, bp can be normal, temperature can low, bp can be high. So look at the temperature. Okay, for low temperature we can have bp low, normal, high. Then for normal temperature we can have the blood pressure low, normal, high. And finally for high temperature we can have the blood pressure low, normal, high. So this is all the instances, and we represent this with x. Oh, so this is the list at this is the table, this is the list. Okay. Now here, a little bit explanation about the notation. It says the entire instance space is represented by x. So in this case, this x column is our entire instance space. This is our possible instances. This column x is the is all of the possible instances, and the individual instance is denoted by xi. Okay. So if you look at the table again, then xi means that put values at this replace this I with values. So xi means from 1 to 9. So x1, x2, x3. Okay, these are the individual values which are represented by xi. Now x absolute, when we enclose the x in the bar, then normally we say that x absolute, it gives the size of the instance space. In this case it is 9, so x absolute is equal to 9. Now the set x is the entire data possibly available for any concept. But it says that in real world problems we don't have the liberty to have access to the entire set x. It means that in real life we will not have this x. We will not have all the individual values of x in our real life. Okay, but if we get all these values, then we will it will be very good for us. Okay, but here it says that instead we will have subset of x known as training data. So if you have the entire set of x, okay, then it means that you have the instance of x. But if you have subset of x, some of the values of x, then it means that you have the training data. It is known as training data. It is denoted by d. Okay, and then we will use this training data on the basis of which we make our learner learn the concept. So if we want our learner to learn the concept, then we will have this data, the training data. Okay. Now, dear students, the what is the concept space? A concept is the representation of the problem with respect to the given attributes. Now, for example, concept 6. Okay, so what we choose previously, we choose previously sk to be our concept. So this is the basic terminology of concept, our basic understanding of concept. Now, dear students, they here it says that example, for example, concept sick defined over the attribute T and BP. So we have two attributes, temperature and blood pressure, and now we want to define our concept sick on the basis of these two attributes. Then the concept space is defined by all the combinations of values of sk for every instance x. Now, what is concept space? Look at the table here. So this is the table, dear students. Before, if you look at the table, we don't have the values of the concept sk. Now here in this table we have all the possible values of concept sk. So if temperature is low, bp is low, then person is not sick. If temperature is low, bp is normal, then he is not sick. If temperature is low, bp is high, then he is sick. So all of these entries are with respect to these two attributes. So this is the concept space. This whole column sk is known as the concept space. Okay. Now, dear students, if you look at the terminologies we discussed, if we move previously, now first of all we discussed what is problem, then we discussed the problem space. Okay. And then we discussed the instance space, and now finally we discussed the concept space. Why we are discussing this? Because we want our machine, we want the symbolic representation of the real world, and basically we try to understand the symbol based learning. So to understand the symbol based learning, you have to understand all these terminologies. Okay, that's why we are discussing this now. Dear student, it says that but there are a lot of other possibilities, and the question is, how many total concept can be generated out of this given situation? And the answer is 2 raised to the power this x. And to see this intuitively, we will make small tables for each concept, uh, and see them graphically if they come up to the number 2 raised to the power 9, since x is equal to 9, x absolute is equal to 9. So with respect to the first step, it says that but there are a lot of other possibilities. How many possibilities? 2 raised to the power 9, which is I think 256. So we have 256 possibilities. Okay, we just discussed some of them. These are not all the possibilities. The total possibilities are 2 raised to the power 9, which is 256. Now, dear students, it says that we will represent all these possibilities with the help of these small boxes like this. So, the representation used here is that every box in the following diagram is populated using Cx of I. Now, what is this Cx of I? The value that the concept C gives as output. So, this is the value that the concept C will give us as output. But what is the x of I? It is basically the input. So you have to provide this input xi, and then C of xi is basically the output which the concept C will give us. Okay. So look at this Cx of 1, Cx of 2, Cx of 3, then Cx of 4, Cx of 5, Cx of 6, Cx of 7, Cx of 8, Cx of 9. Okay. But how much total possibilities? 256 possibilities, because we are talking about 2 raised to the power 9. Now, dear students, in the next diagram, it says that we don't know the concept yet. Okay, because we are trying to find our concept, the basic concept, but we don't know the concept yet. There might be concepts which can produce 2 raised to the power 9 different outputs, such as, so these are the 2 raised to the power 9 different outputs. Begin from C1, then C2, then look at C1 is this, C2 is this, C3 is this, C4, all the way to C raised to the power C2 raised to the power 9. Okay, we have all these possible concepts. Okay, and we don't know the concept yet. What does this mean that we don't know the concept yet? We will discuss this when we move on. So now, dear students, each of the previous is a different concept, which means that this is a different concept, this is a different concept, this is a different concept. So all of them are different concept. but we are trying to identify the true concept. So only one of which is the true concept that we are trying to learn. From all these possibility, we are looking for only one true concept. But what's the dilemma? The dilemma is that we have that we don't know which one of the 2 raised to the power 9 is the true concept of 6 sick. So dear students, here as I said that we will explain what is the concept. Dear student, this is our concept. Basically we want to know concept of sick. Okay, but how much possibilities we have? We have 2 raised to the power 9 possibilities, which is equal to 256 possibilities. So out of these 256 possibilities, we want to identify, or we want that our learner should identify the true concept of sick. Okay. Now here it says that in real world problems we don't have all the instances in the instant space X available to us for learning, as we discussed previously that in the real world you will not have all these possible instances of X. Rather you will have limited instances of X, which we denoted by D. Okay. Now, dear students, it says that if we had all the possible instances available, we would know the exact concept. But the problem is that we might just have 3 or 4 example of instances available to us out of 9. So it's not possible that we will have all the instances. We will have limited instances. In this case, maybe we have 3 to 4 instances available to us out of 9, and then we will have to find the true concept. So dear students, look at the limited concepts, which is denoted by D. So we have just only these instances of x1, x2 and x3. So now dear students, enough for today's lecture. From next video lecture we will begin from the training data set, and we will try to uh, achieve the concept. Thank you.